The question was about this compound, PtCl2En2. The coordination number is 6. And so if it's 6 coordinate platinum, should be platinum 4, not platinum 2. And so that was my mistake. This whole thing should be a 2 plus charge. But since I didn't have that there, I'm glad you got that. I didn't catch that. Okay, thanks. But you're right, James.
Okay.
That would be correct. Okay, the lab starts with anions first or cations first? Cations first. And the lab starts with sodium and ammonium first, correct? Did you guys already prep that?
Yeah.
Good. You're going to prep that, but you aren't going to start there because sodium and ammonium are simple. Well, simple meaning they don't rely on like 20 different steps, right? And so you're going to have that in there, but you're going to do those at the end. And so prep them now, sodium and ammonium, and then we're going to start off with the silver, right? And then go on from there. If you already prepped it, that's fine. You could start with the sodium ammonium test. You're going to have to do that eventually. It's just two things. One is cleaning the platinum for the sodium test is very difficult, and you don't want to do that so often. And so when you get that wire clean, you also want to test the calcium, if possible. That saves you one cleaning step. And some people sit there for 20 minutes and still it's not clean. You know? And so it's a bear to clean that wire. And so the best thing to do is to run the calcium, clean it, so when you burn the platinum, there's no color in the flame. And then you test the calcium first, because calcium gives a very, very faint brick red color. It doesn't last very long. And then test the sodium after that, clean it a little bit. It's easy to clean off the calcium because it burns off so easily. It's a pain to clean off sodium. Because, for example, you wouldn't do this to hot wire, but if you touched everything you touch, do you know that? You leave a sodium residue. And that sodium's easy to detect because sodium is, sodium has a very high sensitivity to the flame test. And so you don't need much. Whereas something like calcium has a very low sensitivity, so you need lots of calcium. And so by the time you get to that step, which is like 20 steps later, hopefully you have enough calcium to see color. A lot of people don't end up with enough calcium to see any color at the end. Well, ammonium is no big deal. Ammonium you can go through really pretty fast. I'll leave it up to you. If you want to do those right off the bat, go ahead. I would start off with the silver. You aren't going to complete, all, how many steps are there? 60, 100 steps, whatever it is. You aren't going to complete those in one lap here. You're going to have to complete, I allotted a lot of days for this. And the reason I allotted a lot of days is because we're going to do it in sequence. First, you're going to run through your known. If you want, you could either work individually or you can work with a partner for your known. And then, you're going to, after you've completed your known, you're going to do your unknown. Your unknown you have to do individually, and it's going to be closed lab manual, open lab notebook. And so you're going to just go off your observation. Are your observations good enough to repeat what you did earlier? But it's not just a repeat of what you did earlier. Your unknown's much more difficult. The reason your unknown's much more difficult is because, or it might be easy, depends on what unknown you get. Reason is because not all the steps are going to work, and so you have to make adjustments. For example, if you didn't have silver, then you shouldn't be adding lots of hydrochloric acid, because if you're adding lots of hydrochloric acid, you're going to screw up the subsequent steps, which is to make it basic. By the time you're done, you have a beaker full of solution, and everything's so dilute, you aren't going to detect much. And so we make adjustments as we go along, and so this is why we have to understand each specific step, which we'll talk about tomorrow, and then make adjustments as we're doing it. This is a lab that, a lot of people come up to me and say, what should I do next? What should I do next? I'm not going to give you much to go. You're going to have to figure out what to do next. For your, in fact, just 1 second. For your unknown, I'm not going to say anything unless it's a dangerous, it's a safety related question. You're going to have to figure out what to do, and you can't talk to your neighbors during your unknown analysis.
Why?
Mm-hmm.
Why?
Why? It's a test. This is your unknown. It's a lab test. That's fine. The first half of this is you can talk to whoever you want. You can use whatever you want. The second part is just a repeat. So can you do it? And then can you make the adjustments to the procedure to do it properly? That's it. All right. Any questions? Any other questions? What's that? Okay, for the anions we do at the end. Yep. So after you finish the cation analysis, then you go to the anion analysis. The anion, the anion, there's nitrate's a dangerous test always. That's the test where some sulfuric acid, concentrated sulfuric acid, splattered out of the test tube, landed on the student's arm and caused a tiny, 3rd degree, like charring of the skin burn. But it was so small, it was okay. So the anion you got to watch out. But anion, there's mixed feelings about the anion because for your unknown, certain combinations of cation and anion are incompatible. Otherwise, you're going to get a precipitate. Your unknowns are all going to be aqueous solutions. More advanced classes will give you a solid, solid unknown, which is harder because you got to figure out how to dissolve it. Maybe it dissolves in water, maybe it doesn't. A lot of this qualitative analysis stuff is, ancient chemistry. This is like alchemy style chemistry to some people because we have instruments nowadays that can detect these at much, much lower concentrations. The instruments, you just got to pay, buy an expensive piece of equipment, then you can do this analysis. And so instead of buying that expensive piece of equipment, you send out samples to the lab. So if I had an unknown, oftentimes, unless it's easy, I wouldn't run it myself. I just send it. When I was working in Santa Barbara, I just sent it to Gardena. There's a test lab in Gardena. You just have to pay. The thing is, at the time, it was about $200 per element that they analyzed. Yeah. Now it's probably way more than that.
Yeah. If you're working with blood, do we have to do qualitative analysis for that? The calcium content, the cholesterol content?
No, that's not qualitative. That's quantitative analysis. When you're working with blood, you want to know how much is in there. Qualitative analysis for us is, can we detect the presence of it? Qualitative analysis is like this. I want to test if my DI water is good. And so one of the things they do in the laboratory is just add a drop of silver nitrate to it. If they get a precipitate, it's no good. It's got some salt in there. Do they care how much? No, they don't care how much. They just know it's bad. And so that's it. That's qualitative analysis. You just want to know, can you detect it? The situation with qualitative analysis is, what if you get a negative? Does that mean you don't have any? No, it just means you can't detect it. You might still have it. It's just so you have to know the sensitivities of each test. For example, lead. Lead, to test for lead qualitatively isn't very sensitive, and so you could easily miss it. Lead and still have lead in there. So you probably want to do something more quantitative for something like lead than qualitative. But definitely, if you see lead there, then you know you have lots of it because detect it. But if you don't detect lead, then it doesn't mean your drinking water is safe. All right, other questions about the quals? So you should prep part. Look at what you think you can finish in a couple of hours, and then just prep that much. But you should definitely prep for this because writing is going to take too much time.
When are we going to weigh the crystals?
Today, not today, but tomorrow. Weighing the crystals doesn't take very long, so you can do that quickly. And then what we'll do is we'll just leave the crystals out so that people can take a look at all the crystals that were, maybe get some ideas about which one is right, you know, or are they all the same? You should take a look in the afternoon. In the afternoon class, some people got some brilliant colorless crystals, big ones. No color at all. Yeah. Maybe that's the right stuff and everybody else got it wrong? No. I don't think so. And then, you know, maybe some judgment about the purity of your stuff. You can take a look at the crystals and then compare it to other people's, and then, you know, if you're making a judgment of the purity, it's purely speculative because, you know.
Is it possible to have a less of a yield with a pure sample?
That's what you want.
Even though it didn't crystallize, perhaps?
Is it a paste?
Not sure.
Some people get paste, you know, they get this liquid tar-like substance at the bottom of the test tube that just won't dry. You know, even after a week, it's still wet, or wet appearing. Some people get that. So take a look, see if yours is dry. The crystals are hard to see because sometimes the crystal is very small. And so, color is always hard to judge. You know what geologists do?
Streak.
Yeah, they do a streak test or a scratch test or something like that to get crystals about the same size, you know. Because when you're making comparisons, you know, like for example, if you look at a crystal of salt, you know, table salt, what color is it?
It's like solid weight, but it's not.
It's not white. If you look at a single crystal of salt, table salt, it's colorless. It's just how light scatters off the crystals, which makes it appear white. But single crystals are usually of white substances are colorless. And so, all right, so we're going to start a long sequence of reactions and separations, and so hopefully the reaction stuff prove to be useful for this lab.
I don't understand what it means to like okay, centrifuge, then wash. Wait, yeah, centrifuge.
We'll cover that. Yeah, everything you don't understand what it means, put a question mark and then ask me tomorrow in lab and I can show you what it means to do it.
Like add the washings to the decanter.
All right, I'll show you exactly what that is. Ask me tomorrow in lab and then I can show you. I'll just demonstrate it.
Yeah, but it just keeps on popping up over and over again in the procedure.
Yeah, it's very important, that particular stuff. This is the ice table we left off with last time, is that right? No? Did we get that? We did copper and tin. Did we finish that problem? Yeah. We left off with this? All right. Let's go ahead and take a look at this one. Initial was 0.100 molar, 6.00 molar, 0 molar. Kc for this is 1.1 times 10 to the 13. Is that correct?
We finished that one.
Did we finish this one?
Yeah, we were on copper 2, tin 2.
Oh, copper 2, tin 2. Okay, did we finish that one? Oh, that's right. Yeah, copper 2, tin 2. Now I remember. This is copper 2 plus tin 2 yields copper 2 plus tin 4. And then the concentrations were what? 200, 200? Wait.
It was 0.100, 0.300, 0.200, 0.200.
Yeah, okay. Okay, did we try the simplifying assumption to solve this? No? Not yet? Okay. When we look at Kc, Kc is 1.48 for this. right? Which means it's slightly biased towards the product, you say? But about even. And so this is about even, right? What did we say the direction of the change was going to be? Because we calculated QC, correct? QC will tell us. You know, it's hard to look at this and say which way it's going to go, like minus, minus, plus, plus, or plus, plus, minus, minus. And so by calculating Q, we figured out it's going backwards. So this is going to be plus 2x, plus x, minus 2x, minus x. Here. And so at equilibrium, we should have 0.100 plus 2x, 0.300 plus x, 0.200 minus x, 2x, right? And 0.200 minus x.
I remember the streak of binomials.
Right, and so something like this, how far off was Q from K? Q was what?
2.62.
2.62, so we're almost there. And so the change should be very small. And so we figured it out. I already wrote all this, right, up here? And so basically KC is going to equal 0.200 minus 2x squared,